G'day everyone, morning. It's Monday morning, week 7 now, so we're getting towards the end of the course. 7? Yeah, week 7 is week 7. So we've only got a couple of weeks left. We're getting to the end of the course. All of this stuff should be an application of what you already know. It shouldn't be telling you anything really new, okay? So if you're striking things new, then you really need to look back into your integration, differentiation, those sort of ideas. This first section across the top, this is just rectilinear motion. Now you probably, if you do physics, you've done rectilinear motion, you've used formulas like S equals ut plus a half at squared, v squared equals u squared plus 2as, and all of those sort of formulas of motion. They all have their basis in mathematics rather than physics, but hey, there's a bit of overlap there. Let's talk about it from a mathematical point of view. Let's just move from our displacement formula with reference to time. If we were to differentiate, I have got it right, Larry. If I was to differentiate my displacement formula, then I end up with my velocity formula or my rate of change of displacement. Rate of change of displacement is velocity, isn't it? Okay. And then if I was to differentiate my velocity, then I would end up with my acceleration, and my acceleration is the rate of change of my velocity. How quickly am I changing my velocity? So that kind of makes sense across the top. And notice the notation that I've used here. I could have here written S dash T and S double dash T. Okay? So whichever form of notation you use, just make sure you understand it. Going the other way, if I'm given the acceleration and I integrate that with respect to time, then I end up with velocity. But remember, I'd need to put a plus c on there, and that would then hopefully be given some information about velocity, and I would be able to find an absolute function here rather than a function with a plus c on it, a generic function. Similarly, if I integrate my velocity with respect to time, and if I have a plus c that I can work out, then I can get back to my displacement function. So all of that shouldn't really be anything new. You should look and go, yeah, that's fine, I get that. I can differentiate one way, integrate the other way, and I'm fine with that. Hopefully that works. Now this is a bit more fun. This is a bit different. Simple harmonic motion. Okay, simple harmonic motion. The best thing to think about is a clock, right? A big grandfather clock, right? With the swing of the pendulum moving back and forth. Ideally, I think it's 1 second each time it hits an extremity point. Now think about this. If I start here, at this point here, all right, let's call, well, it doesn't matter about time so much, but let's call this T0 here. The pendulum's going to swing this way and then stop, and then it's going to swing back the other way. Let's have a look at things that are happening. At this point here, at that exact point, when it hits exactly there, my velocity is going to be equal to 0. Okay, because you think it comes up, stops. Okay, but my displacement, I'm going to call this at, just for the moment, I'm going to call that at -1. Okay, don't get too fussed about the numbers, but this side, -1 displacement. When I hit here, that point in the middle, so it swung here, stopped, and come back to there. At this point here, I'm going to say my displacement is equal to 0, but my velocity, I'm going to put that as the maximum. Because you think about the movement of the arm, right? Can you see how in the middle, it's going to get the most speed as it swings down, max, and then as we go past that point, it's going to slow down because it's now going uphill, isn't it? Because when we get over here, it's then got to have a displacement of 1, but back to a velocity of 0. So can you see how it's kind of moving in this motion, and I can't really do it too well with my arm and keep the speed right, but it gets the maximum speed right here, and then 0 speed there, or velocity, and 0 velocity there. Now, of course, if I want to talk about this velocity max, maybe this way, I'm just going to put a number to it. I'll call that at +1, but when it's swinging this way, it would be going at -1, wouldn't it? Because it's going towards the negative side, okay? Now let's have a think about these things. Those sort of numbers, and they're just numbers, don't get too fussed about the numbers, think more about the meaning of them. Think about the acceleration. The acceleration. Now if you think about this like a, we'll do it this way. Maybe you've got a bowl, some sort of bowl, and you drop a ball bearing in just there. Okay? Can you see that the ball bearing is going to accelerate until it gets to that middle point? Because that's just gravity pulling it down, isn't it? Right? So you drop a ball bearing in there, you place it there and just let it go. The ball bearing is going to gain speed, and therefore it's going to accelerate until it gets to that middle point. Then once it goes past that middle point and it starts to go uphill, it's going to slow down, isn't it? And it has to, because it'll get to this point here. Let's ignore friction and all of that sort of thing. It's going to get to that point there, and it's going to stop at that point, isn't it? And then it's going to start going back the other way. So when it's going down here, can you see how the acceleration is that way? It's getting faster, isn't it? But when we go past that point, the acceleration is that way, because it's slowing down, isn't it? And then it gets to here, it stops. Well, that's because the acceleration was in the opposite direction to the velocity. When the acceleration is in the opposite direction to the velocity, it slows down. And then when it got there, the velocity was 0. And then when it starts going back this way, it's then accelerating, or it's gaining speed, because the acceleration is in the same direction as the velocity. So when we start going back this way, the velocity is increasing. It's now in positive territory because the acceleration is in the same direction as the velocity. And then we will accelerate to that same point where we will hit the maximum velocity. And then after that, the acceleration is in the opposite direction to the motion. So therefore it will start slowing down again until it stops here, and then the whole thing repeats. So we find with this pendulum idea, this ball in the kind of cradle idea, is that it just keeps doing this, right? And assuming there's no friction or anything like that, no air resistance, anything like that, in theory, it would do that forever. Okay, once we moved it this side, gave it some potential energy, let go of it, it would just continue doing that pendulum idea forever. And we call that simple harmonic motion. Now, how can we tell about simple harmonic motion if it is happening? Well, what we need to realise is that when we take the displacement formula and we take the derivative of that twice, so think we'd be here, well then what needs to happen is that the displacement is equal to negative k, I'll explain that, of the acceleration formula. Think about it. K is just some factor, so we don't care about that. But the negative is telling you that these two are in the opposite direction to each other. So when you can differentiate this and get negative k lots of, it's negative k squared, but negative k squared lots of this equaling this, you have simple harmonic motion. Okay? And commonly we write x, two dots rather than double dash, equals negative k squared x. X being displacement, or the displacement function. This is signifying that I have simple harmonic motion because the second derivative is equal to negative k squared x. One of those k's would have come from the first derivative, the other k would have come from the second derivative. Now, why is it negative k squared, and what's going on there? Well, let's have a look at a function that might work for this. If I had something like, and I'll just use y and x for the moment, it doesn't really matter, y equals sine of x. Well, if I take y dot, I'm using simple harmonic motion now, you would agree that sine is going to go to cos x, isn't it? And then when I go y double dash, isn't that going to be negative sine of x? So can you see this notion here, that is that negative value there? If I had some function in here, then when that came out the front twice, that would give me that part, and that is just the original. So effectively, these sort of functions are usually sine and cos functions because of this cyclic nature of sine and cos. When I take the derivative twice, I'm back to the same function, but with a negative out front. So that's why this idea is kind of the guiding light to simple harmonic motion. Now, should this, maybe this got a little bit tricky here for you, but should it largely be tricky? No, it shouldn't, because really, if you can show by taking the derivative twice, it conforms to this idea, you have simple harmonic motion, all right? Once you build into a few questions, you'll get the hang of it. Hopefully this helps. I'll get a question up here in a little while and work one through so you've got sort of some practical to see how to do it. But that's the idea of it, and really this chapter in the book shouldn't be a big issue for you. You should fly through it reasonably quickly, get some answers, understand it. It's likely to be something in the exam, yes, absolutely, because there are some tricky questions with it, but it shouldn't trouble you too much. Hope this one's helped. Catch you later.